Kia ora, and welcome back to lecture 3 of week 4, continuing our study of second order equations. Now this long title here, this looks very similar to the last lecture, but the crucial bit is this bit here. Today we're going to look at inhomogeneous constant coefficient linear second order ordinary differential equations. Now we're going to learn two methods of solving these. We already know some of the theory from before. We know that the general solution is going to look like the complementary solution, which is the general solution to the homogeneous problem, plus the particular solution. So that means we just need to find one solution to this problem, to this equation. And the method of undetermined coefficients is the following. If this function on the right hand side, g of x, is fairly simple, namely a constant, a polynomial, an exponential, trig function, sum or product of those, so a fairly elementary function, then the solution will be of the same type. So if g of x is a polynomial, the particular solution will be a polynomial. So in that case you would just guess an arbitrary polynomial with unknown coefficients, substitute it into the equation and find the coefficients. So if g of x is a constant, what would you try for the particular solution? You'd try some constant. Try an arbitrary constant, substitute it into the equation and find the constant. If g of x is quadratic, then you guess that the particular solution will be some quadratic. We don't know which one yet. Just some quadratic with coefficients a, b, and c to be determined. Now why this works, you can see it already. The right hand side is a quadratic. If y is a quadratic, then the derivative of x squared is 2x, the derivative of x is 1, so the derivatives will still be a function of the same type. That means the whole left hand side will be a quadratic. You'll have a quadratic on the left, quadratic on the right. You can choose a, b, and c to make them the same quadratic, to make it match. If g of x is an exponential, say e to the 2x, you'd try yp equals some constant times e to the 2x. And you can see why it works. The derivatives of e to the 2x are always of the form a constant times e to the 2x. Every term will be proportional to e to the 2x. There's just one case which is a little bit different. If you have a trig function, say sine 7x, then you need to try you need the cosines and the sines. And that is because the derivative of cos is minus sine and the derivative of sine is cos. So when you substitute them into the left hand side, you get sines and cosines, so you'll need both of those to match. Now if this was a complicated function g of x, you might have quite a complicated guess or ansatz for the solution with lots of unknown coefficients in there, but it will still work. Later on, now this may still seem a little bit like cheating to you, just guessing the solution, but it's not really, but certainly this won't work for all functions g of x. In that case, there is another method, which we will get to later on, which is more systematic and works for any g of x. Okay, so I'll mostly introduce this through, I've said all of that already. I'll introduce this through examples. So here we go, y double prime minus 4y equals x squared. So the general solution is yc plus yp. To find the complementary solution, write down the indicial equation, solve it, m squared equals 4, m equals plus or minus 2. So the complementary solution is c1 e to the 2x plus c2 e to the minus 2x. That's nice and easy. Now, the right hand side is x squared, but I can't guess just x squared. You'll see in a second that I need, for the particular solution, I need to take y equals an arbitrary quadratic. ax squared plus bx plus c. I'll need to get the derivatives ready. Y prime is 2ax plus b. Y double prime is 2a. And now I am ready to substitute those into the original equation, including the inhomogeneous term. So I get y double prime minus 4y is equal to 2a, that's the y double prime term, minus 4 ax squared plus bx plus c. And this must be equal to x squared, and it has to equal x squared for all x. In other words, the function on the left has to be literally the function x squared. So I match coefficients. There must be the same polynomial on both sides. The x squared term on both sides. What's the coefficient of x squared on the left? There's only one term, it's only that one. Its coefficient is negative 4a. Coefficient of x squared on the right is 1. Coefficient of x on the left is negative 4b. Coefficient of x on the right, well, it's 0. There aren't any x terms. The constant term on the left, the constant term is 2a minus 4c. On the right, the constant term is 0 because there isn't a constant term. So this is 3 equations and 3 unknowns, a, b, and c. And if all goes well, I can solve them. Now, in the general case, you would have to use row reduction, Gaussian elimination to solve for a, b, and c, but this is a very simple set of equations. A is minus a quarter, b is 0, and c is a half a, so that's minus 1/8. So I'm done. I know the general solution of this differential equation. It's c1 e to the 2x plus c2 e to the minus 2x plus the particular solution, which is negative a quarter x squared minus 1/8. All done. Now this particular equation didn't have any initial values, so we just stop when we've found the general solution. Okay, so that was a polynomial one. Now an exponential one. Again, same setup. Start with the indicial equation, m squared plus m minus 2 equals 0. I could use the quadratic formula, or I could factor it. What's that one going to be? That's going to be m plus 2, m minus 1. So m is either negative 2 or 1. So I'm in case 1, 2 distinct real roots. So the complementary solution, c1 e to the minus 2x plus c2 e to the x. Right hand side is an exponential. So for the particular solution, I just guess y is some constant times the same exponential. So e to the minus x. Y prime is going to be negative a e to the minus x from the chain rule. Y double prime is a e to the negative x. So once again, I think I've probably said this already, but you may well need to brush up your calculus, differentiation, and integration, because that's going to be your bread and butter when you use these techniques of solving differential equations. Substitute into the differential equation, I get y double prime plus y prime minus 2y. What does that come out to be? Y double prime is a e to the minus x plus y prime, which is negative a e to the minus x, minus 2y, which is negative a e to the minus x, equals original right hand side up there, 3 e to the minus x. This time it's just it's very easy to solve. It's just one equation and one unknown, and in fact those guys even cancel. Then I have a common factor, e to the minus x, which is not 0, so that cancels. So I get negative 2a is equal to 3. A is equal to negative 3 halves. But as you practice this, each problem is slightly different. You will need to do a fair number of them to get good at it and to see what little issues can come up. But remember that you're solving for the coefficients, not for x. So the general solution is y equals c1 e to the minus 2x plus c2 e to the x minus 3 over 2 e to the minus x. That is done. Okay, and the last one is cosine on the right hand side. Start with the indicial equation. So we're solving the homogeneous problem. Well, that one is a perfect square, so that has a double root. So this is the case of a repeated root, so the complementary solution is c1 e to the minus x plus c2 times x e to the minus x. To get the second linearly independent solution, we multiply it by x. I've got a cosine on the right, so for the particular solution I take some cosines and some sines, and I get my derivatives ready. That's going to be negative 2a sine 2x plus 2b cos 2x y double prime equals negative 4a cos 2x minus 4b sine 2x. So be very careful with your sines and cosines and all the plus and minus signs. Substitute into the differential equation y double prime plus 2y prime plus y. What do I get? Well, it's going to be 6 terms, so I have to be a little bit careful writing them all down. Negative 4a cos 2x minus 4b sine 2x. That's the y double prime term. Plus 2 times y prime, negative 2a sine 2x plus 2b cos 2x plus y plus a cos 2x plus b sine 2x, all has to equal the original right hand side up there from the differential equation, 100 cos 2x. Now, I could simplify the left hand side by collecting all the sines and cosines first, but notice that every term on both sides is either a constant times cos 2x or a constant times sine 2x. And because sine and cos are linearly independent functions, the coefficients of each of those functions must match. So I'm just going to match coefficients again, and that will help me minimize the total amount of writing I have to do, because each time you write out an equation you have a chance of making an error. Match coefficients. So the coefficient of cos 2x. On the left hand side I've got negative 4a. You just run your eye along and write, whenever you see a cos term you stop. There's 2 times 2b, so plus 4b plus b. Sorry, plus a. I'm doing the cosines. Negative 4a plus 4b plus a. And on the right, what's my coefficient of cos 2x? It's 100. Now write down the coefficients of sine 2x on both sides. Negative 4b, negative 4a, plus b. What's the coefficient of sine 2x on the right hand side? It's 0. So you never do anything with those trig functions. You never use trig identities or anything. You just keep them as they are. So what have we got? We've got negative 3a plus 4b equals 100. And negative 4a minus 3b is equal to 0. So 2 equations and 2 unknowns. Okay, I'll let you solve those equations by Gaussian elimination. I'll just write down the solution. Comes out to be a equals negative 12, b equals 16. So the general solution is y equals c1 e to the minus x plus c2 e to the c2 x e to the minus x minus 12 cos 2x plus 16 sine 2x. So even though the method did rely on guessing the form of the solution, it does work, and we have solved quite a difficult differential equation, and we have found the general solution. Now there's one little catch which I won't explain here, but I will leave it to you as a question to either think about or maybe look up in the textbook. Something can go wrong with the situation I've described, and that is, what if one of the terms in the particular solution that you write down is actually a solution of the homogeneous equation? Then when I substitute it into the left, I'll get 0, and there's no possibility of it matching any term on the right hand side. So what would happen then? running out of space here. What if one term in yp is a solution to the homogeneous equation? Then I would need to change my guess a little bit, and that's your challenge problem. What do you change it to?